Okay, so welcome back to the 19th class. So, before we go into the calculation of partition function for paramagnetic samples and then on to discussion of paramagnetic systems, I would like to remind you, I want to tell you that in this curve, when uh, when h by t is relatively small. Uh, uh, so here you see a linear increase of the magnetization. So like magnetic moment per spin into n is magnetization for the entire sample, and that goes as 1 by t, right? So if you switch on H field, keep it constant and increase the temperature, then M essentially ST increases, magnetization decreases here. So here T increases in this direction because as T increases, it would go to smaller values. M decreases. So that's basically going down like this, right? And this behavior of magnetization per mole, if you like, per unit quantity, if you like, per magnetic moment, per mole, per gram, whatever, and its decrease as 1 by T is known as the Curies law, right? Whereas, as we discussed later, in last class, that chi actually goes as 1 upon T minus Tc, and that is the so-called Curie-Weiss's law. Of course, that's only above as T approaches Tc. So above the Curie law, it goes as T minus Tc, and that is the Curie-Weiss's law. So I don't remember whether I said it in the last class or not. So this is the Curie's law and the Curie-Weiss's law, which was observed experimentally, and our aim is to explain, understand that from the microscope picture by calculating the partition function or whatever relevant. So, discussing about paramagnetism. Paramagnetism consists of a lattice, and well, you could also have a paramagnetic gas, and that has a different name. But at the moment, as of today's class, we are discussing that its spin can be either up or down, and they are not interacting with its neighbors, right? And you have other terms in the Hamiltonian, but we are focusing only on the spin magnetic moment interaction. This was the Hamiltonian HSS for spin. We are focusing only in the presence of a magnetic moment and in the presence of an externally applied magnetic field. Let's for simplicity assume that the magnetic moment can point only up and down, so it's quantized in that sense. Assume half spin, then the probability that the system uh, can take some energy uh, from the environment, right, to point the same direction. Uh, well, it doesn't need to take energy, but I mean the probability that a particular magnetic moment, since they are uncoupled, we can talk about individual magnetic moments, then multiply it by n to get the total magnetic moment. So the probability that you have a microstate, or you have a microstate for one particle where it is pointing up, is some proportionality constant, which is of course the partition function, or the 1 upon the partition function, into e to the minus beta e, and e comes with a minus sign. So since energy is negative, it becomes beta mu h, where beta is of course kVt. And the probability that the spin is pointing down is c 1 by z, if you like, e to the minus mu b kVt, right? Because it's positive energy cost. So for one spin, if you can write down, if you had one spin, the entire system consists of one spin interacting energy, exchanging energy with the environment, then the partition function of one spin could be written down as e to the minus mu b by kBt plus e to the power plus mu b by kBt. This corresponds to the case where the magnetic moment is pointing the same direction as p, and then you have a minus sign here and minus beta here. So mu b by k. So the probability that a particular microstate of one spin will point in the same direction as the B field will be e to the power mu b. So here the b is missing because in class I had written h. So it's mu b by kbt, right? And this is the partition function. And the probability that a spin, an individual spin, will point down is e to the power minus mu b by kbt, and this is the partition function. Now, as we shall understand a bit later, since these are uncoupled spins, I mean, so it doesn't really matter what is the, so we'll see a bit later that the partition function of the entire system can be written as Z1, the partition function of an individual system, to the power n, n being the n spins. Okay, and note, since these particles are sitting at individual lattice points, right, you can't exchange the position of each of these degrees of freedom. So hence the partition function of n spins comes without the n factorial. On the other hand, if they were a gas where magnetic moments could exchange positions with each other, right, then you might, I mean, you had also position degrees of freedom. Suppose you had also the position degrees of freedom. You accounted for the position degrees of freedom. Then you would have an n factorial extra. But here, basically, we are not worried about the position degrees of freedom. At each point in space, there is a certain magnetic moment sitting, and you can't exchange their position. So the partition function becomes Z1 to the power n. Okay, and that's possible because each particle or each degree of freedom is independent of the other. So each spin is independent, fixed at lattice center. So we could, after that, very easily write down the magnetic moment per spin, right? And mu1 is the average, is the ensemble averaged. Ensemble here, I mean, ensemble is up and down, but in general, ensemble is of course for n particles, right? And we'll see that. Right? So for one particle, mu1 is equal to the magnetic moment so the value of the magnetic moment when the spin is in a microstate where it is pointing up in the same direction of b. So mu into probability of that microstate where this is this and the z, e to the power mu b by kbt upon z is the probability that the system is in a microstate where its spin is pointing up. And what is the value of the magnetic moment there? It's mu. Plus, when the spin is pointing down, then its magnetic moment is minus mu. Hence, we have written this minus mu here. Right? So it's plus minus mu into probability of accessing that microstate, which is e to the minus mu b by kbt. And this quantity is by the partition function is the probability of occupying a microstate individual spin when it is pointing down, right? And this is essentially this quantity e to the power, I mean, if you write mu b by kbt, take it to be x, e to the power x, e to the power minus x, and you take out minus mu. This is essentially sine hyperbolic. This is essentially a sine hyperbolic function if you divide it by 2, and this is a cos hyperbolic function. And here you would divide by 2, here you would divide by 2. So this is sine hyperbolic by cos hyperbolic. So the magnetic moment of one spin is mu tan hyperbolic mu b by kbt. Okay. Now each of these spins are independent. So if this spin has a certain probability of pointing out, I mean, if you basically ensemble average equal to time average. So if you look at a particular spin, It is a certain probability of pointing up, certain probability of pointing down. If you keep on looking at it for a very long amount of time, you calculate how much time it is up and how much time it is down, and you basically calculate the ensemble average. So that's one way of thinking. That's actually one way of thinking. But what is your actual ensemble? It's basically you have n particles. Depending upon probability, a certain number of particles is pointing up and a certain other number of particles is pointing down probabilistically, and you're taking an ensemble average. You're taking all microstates. Suppose particle 1 is up at some point, particle 2 is down at some point, particle 3 is down at some point, and so on and so forth. That would be one microstate. One other microstate would be this is down, up, say. The second one is up, third one is down, and so on and so forth. That would be in the microstate. So how many microstates on an average, right? On an average, depending upon probability, you will have a certain number of spins pointing up and a certain number of spins pointing down. Right? But of course, it is possible that all spins are pointing up. That is one microstate. All spins are pointing down. That is another microstate. And there will be an energy of that microstate. Right? And you will say, oh, all spins pointing down, the probability of accessing that microstate is so much, depending upon the energy by kBt. Right? But it can also easily be calculated that since these are non-interacting, you say take the probability of one particle multiplied by n, and that is the average number of average value of the magnetic moment of the entire sample. So it's n magnetic moment with n spin is n into mu, because each spin has a certain probability of pointing up and down, and there's a mean probability, average value of the probability is n mu tan hyperbolic. What's the behavior of tan hyperbolic mu h by kBt? So it's e to the power x minus e to the power minus x. So this is the function, okay, tan hyperbolic. When x is small, when would x be small? When kBt is much higher than mu b. So this energy scale is much higher than this energy scale. This is small and this is very high. Then x would be small. Then these exponentials can be written as 1 plus x minus 1 minus x. And similarly here, right? And that was 2x by 2 into x. That is the behavior of tan hyperbolic. In that case, what would be the behavior of mu n? Expectation value, average value. Right? This is called the expectation value. It will be n mu into x. Right? So this is the expectation value of one spin and n into that, and then n mu, right? And the value x is this thing, the mu b by kBt. Mu b by kBt, mu by kBt was x, and that is extremely small, right? So the magnetic moment of the entire sample is n mu into an extremely small value. So because mu b is much smaller than this, right? So that's the magnetic moment per spin, right? When x is large, when mu b is much larger than kBt, then what would you be? Then this will be a large quantity, e to the power x will be a large quantity, e to the power minus x will be a very small quantity, both here and here. Right? So what do you have? This tan hyperbolic will saturate to the value 1. And what will be the magnetic moment of the entire sample? So into n. It is mu, n mu into e to the power x into e to the power x. This should be 0 again. This is n mu. Right? It's some constant value. So here it means that even as you change, if you change the value, so this is essentially a static. This is at high values of mu b by kbt. When magnetic field is very high, then the total magnetic moment of the sample becomes nearly constant. It's not changing, and that's because all spins are anyway most of the spins are anyway pointing in the direction of the magnetic field. That's how this will be, right? On the other hand, when x is small, is less than 1, then the magnetic moment, if you had fixed magnetic field, goes as 1 by t. So magnetic moment goes as 1 by t, right? So what is the magnetic moment? And of the entire sample, of course, you can calculate it per particle also. So that is mu square b by kbt. That is m, right? That's the magnetic. This is magnetic moment. This is capital M if you're in magnetization. Del m del b is n mu square by kbt. You are taking a derivative with respect to b. So chi, which was del m del b, the Puris Law, chi goes as 1 by t. Here you see its value is n mu square by kbt. Right? So this is magnetization, but even if you took a derivative with respect to b, then this quantity n mu square by kbt would be chi, and that in turn will go as 1 by t, which is Puris Law. This is why Puris Law is valid. Here, of course, I plotted m versus b by t. Okay. Just to remind you, what was this mu? This mu is, I mean, if you know the magnetic quantum number, S max, the spin, it can go as plus half and minus half to mu 0 g. Right? The Bohr magneton, the Lambda g factor. So all that is put inside mu here. So what do you get? So this is the how the tan hyperbolic looks. Here it goes as proportional to mu b by kbt, right? And here it is saturating, right? And that is exactly, if you remember, this is how it looks. Of course, here you had different values of J, right? Maximum. We'll look at that soon. But this is essentially, I mean, for spin half, you had just plus half and minus half. Well, this is for chromium, C by 2. But if you had half, this is the broad look of the magnetization versus H by T. And that actually matches. Right? The tan hyperbolic, I mean, you can check out how tan hyperbolic looks, and you can see whether it matches or not. Right? Next, what we calculate? We can easily also calculate the average energy of the system, and for that, we do initially for one spin and then for n spins. So average energy for one spin when it is pointing up is minus mu b into probability of accessing that microstate for one particle plus mu b, that's the energy when it is pointing down, into probability of accessing that microstate. This by this is the probability of accessing that microstate, right? And the energy of n particles and such non-interacting magnetic moments is n into e. Okay. So if you like, so even qualitatively speaking, what one could say, I mean, looking at the energy, and I've plotted it as the function of temperature. At very high temperature, for reasons that we discussed in the last class, qualitatively, equal number of spins are pointing up and down. So energy will be, if you like, mu b, and then so basically minus mu b by kbt plus mu b by kbt. So all that I've done is divided E1 by kBt, but otherwise it will be plus mu b and minus mu b. And the probability of up and down, up state and down state at very high temperatures is nearly the same, slightly different, but nearly the same. So you're going to see equal number, and so that's talking about one spin, but if you have n spins, then almost an equal number of spins will be pointing up and down. There'll be, of course, always a slight bias towards the up spin. Only at equal to infinity will you have equal number of up and down spins, but nearly the same. Hence, the magnetic moment would be nearly zero, and also the energy of the entire sample, only the magnetic energy. I'm not talking about lattice energy, other energies, only the magnetic contribution to the energy will be again zero, because you have minus mu b and plus mu b, and the probability is the same. So half of the spins are pointing up and down. On other hand, and this is not going to change, it's nearly like constant, right? I mean, if you go on increasing temperature, the average number of spins pointing up and down, you mean nearly equal. That's on the other hand, at very low temperature, when mu b is much greater than kBt, then all the spins are pointing in the direction of B. Right? So even if you change temperature slightly, nothing much is going to happen. I mean, all of them are already saturated. Only a small number are going to flip and take, release energy and flip uh, as you go down in temperature. So this the total magnetic moment, as well as the energy, is nearly fixed, not exactly, but nearly fixed. Right? So that's this case. In between, when mu b and kBt are comparable, that's when the changes in the system happen. So this is nearly a frozen system. A frozen system, but I mean, it's not frozen. That a spin which is pointing up in the next moment can point down. Similarly, a spin which is pointing down can point up. So in that sense, it's not frozen. My individual uh, each particle can change its microstate, but on a whole, with n particles, equal number of spins are pointing up and down, and in that sense, frozen. But here, most of the spins are pointing up. Now we can also write E1 by kBt is minus mu by kBt plus mu by kBt, and of course, this is already x. So x is mu b by kBt, and here we can write e to the power x and e to the power minus x, where x is mu b by kBt. And this helps us to write it as, I mean, by introducing this extra kBt, we can write this as minus x plus x. Right? We can take minus x out. We can write it as e to the power plus x minus e to the power minus x. Right? Of course, by the partition function. Now, when mu h is much smaller than kBt, kBt is very high. That's when x is much smaller. Right? And and then, of course, this z is a constant factor, of course. Then we can write this as wait, there has to be a z factor as well. So, but